In the use of Hilbert spaces, there are several specific types of linear operators that are very important. Over the next few sections, we're going to look at these. Shortly, we will introduce the identity operator. Other important types of operators include inverse operators. Finding these often solves a physical problem mathematically, and they're also important in operator algebra. Unitary operators, which are very useful for changing the basis for representing the vectors and for describing the evolution of quantum mechanical systems. And Hermitian operators, which are used to represent the measurable quantities in quantum mechanics. Hermitian operators also have some very powerful mathematical properties. As I said, we're going to start here by looking at the identity operator. Now, at first sight, it might seem that this operator is of little use. Operating on a function with the identity operator does absolutely nothing, of course. In that sense, it's like multiplying a number by the number 1. However, the identity operator turns out to be very useful for some algebraic manipulations and for performing various specific kinds of proofs. So let's see how we construct it and how it works. The identity operator, which we typically write with a letter I with a hat on top of it, is the operator that, when it operates on some vector or function, leaves it unchanged. In matrix form, the identity operator could be written as follows, with 1s all the way down the diagonal and 0s everywhere else. In bracket form, we're going to propose here that this identity operator can be written in the following form. The identity operator is equal to the sum over I of the ket vector psi I times the bra vector psi I, the same I, same index in both of them. And these psi I form a complete basis for the space. That's actually mathematically very important. This summation here must be over a complete basis set. So let's prove that. We're going to take an arbitrary function f and expand it as usual with expansion coefficients, and we know what any given expansion coefficient is. If we want to find the expansion coefficient Cm, we take the inner product of the bra vector psi m with the function as a ket vector. So if we make that substitution, we can rewrite the expansion of f in this form with these as the expansion coefficients. Now, with our proposed form, then I operating on f, of course that's just all of this operating on f, but this entity here is just a number. That's an inner product. So we can move it about in the product. Hence, we can rewrite this, moving this in front of the psi I. So we've now got it here in front of the psi I ket vector. And hence, using this fact that we already know that the vector f is this expression, this looks the same as the expression we've got here. So therefore, we've just proved that I operating on f gives us f. And f was completely arbitrary. So now we've completed our proof. We've actually proved that this form that we had here for the identity operator is in fact correct, because I operating on any function f just gives us f. Now, the statement that the identity operator I is just the sum over I of this ket vector for I and this bra vector for I is trivial if psi I is the basis used to represent the space. What do I mean by that? Well, if we are using the psi I basis to represent these vectors, then rather trivially, psi 1 is just the vector 1, 0, 0, 0, and so on. And therefore, the outer product of psi 1, the ket vector, with psi 1, the bra vector, the product of these two vectors then, is just this rather simple matrix with a 1 here and zeros everywhere else. Similarly, if we look at the second vector here, it would give an outer product that looks just like this, with a 1 here and zeros everywhere else, and the third one would have a 1 here and zeros everywhere else. And so rather obviously, this construction here just gives us this matrix with 1 down the diagonals. And that's what we knew we wanted. So that's not a surprise. But if we are talking about this same operator here, and the basis we're using to write down these vectors is not itself this basis set, then some specific psi I is not a vector with just the ith element being 1 and all the other elements being 0. In fact, in general, this matrix that we would get by taking the outer product of psi I with itself, in general is a matrix that possibly has all of its elements non-zero. But nonetheless, the sum of all of these matrices here still gives us the identity matrix. That's part of the power of this particular proof that we've just done. So maybe these psi I are the energy eigenfunctions, but we're expressing all the vectors for the moment using a momentum basis, maybe a set of plane waves for some problem that doesn't have a uniform potential, so that the energy eigenfunctions and the momentum eigenfunctions are not the same. In this case, this matrix here would not be just a very simple matrix with a 1 in one diagonal element and zeros everywhere else. But still, the sum of all of these matrices would give us the identity matrix. So we can use any convenient complete basis to write the identity matrix. Now, this expression here has rather a simple meaning when we think about it in terms of vectors, when we visualize it using our vector way of looking at things. In this expression here, this number is just the projection of the vector f onto this axis, the psi I axis. So multiplying this unit vector along this psi I axis by this number, that is this object here, we could write it like that if we want, gives us simply the vector component of the function f on the psi I axis. Provided that these psi I form a complete set, then adding all of these components up again just reconstructs f. So we're breaking f down into its vectors, the components along each of the axes here, and then adding them all up again so we get back to the same vector. That's what this expression is going to do for us, this expression here with the f in it. Remember that the vector in our space is the same vector regardless of which set of coordinate axes we choose to use to represent it. If we think about the identity operator in terms of vectors, then the identity operator is that operator that leaves any vector unchanged. Again, we can choose any coordinate axes we like and then project our vector out onto those axes to give a set of component vectors. Then we can add all those components up again to reconstruct the original vector. That is what the identity operator is doing in the algebra we have constructed. It does not matter which complete set of coordinate axes, or more rigorously, which complete basis set that we use in thinking about this operation. The identity operator can be expressed in any convenient complete orthonormal set. Now, you may still not be convinced that we've done anything useful here. You may still be thinking essentially that all we have done is proved 1 equals 1. Perhaps you'll be more convinced once you see the use of this identity operator in the following mathematical proof of a rather important result. This proof also shows the elegance of the Dirac notation. We're going to prove that the sum of all of the diagonal elements in a matrix or a linear operator, what is sometimes called the trace of the matrix or operator, is not changed if we change the basis used to represent the operator. Now let's use the identity matrix then in this formal proof. Since the identity matrix is the identity matrix, no matter what complete orthonormal basis we use to represent it, we can use the following algebraic tricks. First, in some proof, we're going to be able simply to insert the identity matrix in some basis that we like into an expression, because it doesn't do anything. Then we can rearrange the expression and find another identity matrix buried in there, and we can take out that result. And quite often, this is a very useful trick to do and enables us to conclude all sorts of interesting things. So let's look at the proof that the trace of an operator is independent of the basis. Consider this sum, S, of all of the diagonal elements of an operator A. And we're going to be writing the operator A on some complete basis here, psi I, an orthonormal basis. So here is what the sum of the diagonal elements are. We remember that these were the expressions for the elements of an operator as a matrix, and in this case we're looking at the diagonal ones, which are the ones which have the same index for the rows and the columns. So the sum of all the diagonal elements of the matrix is a sum over I of all of these elements, which are the diagonal elements, because I is the same here on both sides. Now, suppose that we have some other complete orthonormal basis that we could use. So maybe this was the energy eigenbasis, and maybe this is the momentum eigenbasis, for example. We are postulating that since this is a complete basis, we can also write the identity operator like this if we want to. So in this summation here, let's just insert an identity operator just before A. That makes no difference to the result, since the identity operator operating on A is simply the same as A. It makes no difference to anything. So we have, with this identity operator inserted in here, and using this particular version of the identity operator on the second basis, we can make this substitution. And then we can start rearranging things. So we take this expression that we had and then reorder the sums. So we had the sum of M inside here and the sum of I out here. We can flip those round. And we can move this number now that is inside the summation here. We can move it from this side to that side if we want to. And then we can move this sum I in here because there's nothing out here with an I in it. And we recognize that when we've done that, we can regroup our terms, these psi i's here. We can regroup them. And we recognize that this collection here is simply the identity operator. So we can replace it with the identity operator. The identity operator this time expressed on the basis psi I instead of the basis phi I or phi m that we were working with before. So now we have, starting from here, and we have now got to this point down here, the final step is to note that an operator operating on the identity matrix is just the same thing as the operator because the identity matrix does nothing. And so finally, we have proved the following. Hence, the trace of an operator is the sum of the diagonal elements. It is independent of the basis used to represent the operator. These are diagonal elements when we're working on the phi m basis. Maybe those are the momentum eigenfunctions. And these are the diagonal elements when we're working on the psi I basis. Maybe those are the energy eigenfunctions. But the trace of the operator, the sum of the diagonal elements, is the same no matter what basis we're working on. And we've proved that using the identity operator here and that neat little trick I showed you. And of course, this fact that the trace of an operator does not depend on what basis you express the operator on is why the trace is a useful operator property.